Let's get started then. All right, so here's our a quick review of the chain rule. Okay, so when we write it out as a derivative rule, there's two different ways that we can write the chain rule. One way is to say that I have some composition, right? So something like h of x is f composed with g of x. Okay. Then h prime of x is f prime with g plugged in times g prime of x. Okay. There's another way to write this. I could also have written let y equal, well, here, let's back up a second. Let u equal g of x and y equal f of g of x. Since g of x is u, I could write this as f of u. Okay. So then if I want to find the derivative of y with respect to x, the chain rule says take the derivative of my outside function, which in this case is y, but the input is g of x, which is u. So I'm taking the derivative of y with respect to u, and then multiply by the derivative of g of x. Well, g as a function is u, so I'm taking the derivative of u, and its variable is x. Okay, so this is another way of writing out the chain rule. Okay, so let's just do a quick example where we write it out using this Leibniz notation. All right, so as an example, let's suppose that I have a function, and we won't make this too complicated. We'll just say something like sine of x cubed. Okay. And I want to find dy dx. Now, I deliberately chose a function that's very simple, so this would be easy to do. What I'm going to do is illustrate this using the Leibniz notation. Okay, so that's not the quickest way to do this problem. I'm just picking this, as an easy example. So what I can do is I can say let u equal x cubed. Okay, so then y is the sine of u. Okay. So then if my derivative formula dy dx is equal to dy du times du dx, then I need to find these two pieces. Okay. If u is x cubed, then the derivative of u is 3x squared. Okay. If y is the sine of u, then the derivative, where I treat u as my variable, is just cosine of u. Okay. So then this is going to become cosine of u times 3x squared. But I don't want to have two different variables in my answer. I started with x's, so we go back to x's. U is x cubed, so I just write this as cosine of x cubed times 3x squared. Okay. Now, this is probably a little bit more writing than you would typically do on this problem because we've sort of written out all of this extra stuff over here that you might not do, but I'm using this as an example. And when we go forward to implicit differentiation, sometimes this is very helpful for keeping things straight. All right, so that's our quick review of implicit differentiation, or of the chain rule. All right. So now let's start section 3.8 on implicit differentiation. So when I start this section, we're not going to start by differentiating. We're going to start with this other side and figure out what does this implicit part mean. And then we'll get into, what is an implicit function, and then we'll take derivatives of it. Okay. So what I'm going to do is I'm going to start by showing like a regular function, right? So like y equals x squared. When I write this, and when I graph it, right, I think of this as being like a normal function. So here, y is explicitly a function of x. Okay. If I were to write something like x squared plus y squared equals 4, okay, and we'll draw a graph. That's just a circle centered at the origin with a radius of 2. Okay. This is not written like y equals a function of x. However, if I give you a value for x, you could probably figure out a value for y, right? So for example, if I said x is 2, you could solve for y and compute what it is. Or if I said x is 1, you could solve for y. But because of the squared, when you solve for y, you have to take a square root, and you might get 2 answers. Okay. So we don't exactly have a function. And you can also see that with the graph, right? On the graph, it doesn't pass the vertical line test, so it's clearly not a function. Okay, however, we still want to be able to work with something like this. We still want to say, oh, I can look at this. I can draw a graph. I want to be able to do calculus on it. I could still look at a point on this circle and compute a tangent line. So, I should be able to do that type of thing. And all of my rules require me to have functions, so how do I get around that? And the way that we do that is I could think of this whole graph as not a function. But if I were to break it into smaller pieces, the individual pieces I could write as a function, right? So if I take x squared plus y squared equals 4, right, and I restrict my domain a little bit, maybe I only look at y values that are positive, right, or we'll say greater than or equal to 0. Okay, this graph is a function. So here, y is greater than or equal to 0. This graph passes the vertical line test. Okay. And then if I also draw x squared plus y squared equals 4, where y is strictly less than 0, okay, then this one also passes the vertical line test. And so what I have is a graph where I need 2 different functions to make up the graph, but if I break it into 2 functions, then they're both functions, and I can do calculus. And then we could do things like find equations of tangent lines. Okay, so in this case, x squared plus y squared equals 4 could be written as 2 functions. Okay. Now, the way that I broke it up seems kind of natural and it's very easy, but it's not the only way that I could have broken this up. So the way that we break up a function is, or that we break up, an equation into functions certainly is not unique. And I could also end up with a graph or with an equation that would be more challenging to break up, right? So like, for example, this one, if I wanted to write the graph of this top and bottom piece, what I could do is I could solve for y, right? So like y squared equals 4 minus x squared. And then when I square root, I get the positive square root, and I get the negative square root. And that corresponds to these two pieces. So again, it's pretty natural just because the way that I would solve this equation for y would lead me to get these two pieces. Okay. But I could break this up into separate pieces in other ways, right? I could say that this is one of my pieces. That is a function, passes the vertical line test. This is a function that passes the vertical line test. So these two functions also make up x squared plus y squared equals 4. Okay, so why are we talking about this? Well, we want to talk about a graph that's not explicitly a function. And we said sometimes we can break it up into more than one. What we have to be careful about is that the way that we do that is not unique. So we want to be aware of that. Okay. The second thing is sometimes the way that we can do that is not easy or obvious in any way. Okay. So let me give you an example of a function. Let's suppose I have something like x squared plus sine of xy equals e to the y squared. Okay. It would be really, really challenging to try and solve this for y. I'm not saying that it's impossible. I'm saying for our Calculus 1 course that this isn't going to happen. So we can't solve this for y. And there's certainly ways to write functions that can't be solved for y and get, you know, a nice explicit formula. Okay. And actually, well, so the question is, can I still do calculus on this? If this creates a graph that I could look at, can I still find things like tangent lines and things like that? And the answer is yes. It turns out that it doesn't matter if I have something, okay. It doesn't matter if I have something, you know, that's simple or complicated. The way that we deal with this is always going to be the same. The real trick is that when I'm finding the equation of a tangent line, you know, say I have it on the circle here, if I zoom in closely, does it look like a function nearby? And if I just look really closely to that point, right, then I just see this bit of curve, and that's okay, that looks like a function. And it doesn't matter if I break it up in sort of a natural way or in a crazy way, or if I don't really know how to break it up at all. As long as it looks like a function close to that point, it will act like a function, and then we can do our calculus on it. Okay. So if the graph of an equation looks like a function, near a point, then we can take a derivative near that point. All right, or I should say, then it acts like a function near that point. Okay, now we still have the same limitations, right? So I can draw a regular explicit function that doesn't have derivatives at certain points. Okay, and same would be true here. But as long as it doesn't have the sharp corners or the vertical tangent lines and looks like a function, then it will have a derivative. So if a function or if a graph looks like a function, near a point, and is what we call smooth, right? No sharp corners, no vertical tangents, then we can compute a derivative at that point. Okay, now, the way that I've written this doesn't sound like the way I normally write a theorem. It's not as formal as a normal theorem, and it's because what I'm writing here is something called the implicit function theorem, and that's a little bit beyond a Calculus 1 course, okay? So we want to be able to do implicit differentiation, but talking about this idea of functions acting like, or a graph acting like a function, that gets very complicated to write down explicitly, okay? And we're not going to do that. We're just going to kind of take advantage of this thing that exists and say, all right, implicit functions are a thing, and as long as it looks like a function, it'll act like a function, and I can treat it like a function. Okay, so let me just show you some examples looking at graphs. Okay. All right. So we're going to illustrate 3 points. I'm going to have a point A, a point B, and a point C. Okay. So at A, we can compute a derivative. Okay. If I were to zoom in around the point A, right, and we'll just pretend that I've zoomed that in, then my graph looks like, you know, just some curve that looks like a normal piece of a function, you know, with my A living on it, and that's fine. Okay, if I zoom in to B, it doesn't matter how closely I zoom, that graph crosses over itself. So no matter how closely I zoom in to the point B, I'm always going to get a graph crossing over itself, which will fit. It'll fail the vertical line test. So at B, the graph never looks like a function, no matter how closely we zoom in. Okay, so no derivative there. Okay, at C we have sort of a different problem. If I zoom in around C, the problem is that my tangent line looks vertical. Okay, so that's going to create a problem there. Okay, so when we talk about implicit differentiation, it's really important that we talk about what point we're taking a derivative at, because it's not that a function is either good or bad. A function or a graph can have good and bad points. Okay, just like we knew before with functions, right? Some, you know, you could take derivatives at some points, but not others. All right, now let's talk about how do we go about taking a derivative. Okay. So now let's look at, this is called implicit differentiation. this is the how, instead of, like the theory. So I'm gonna go back to our really simple example of a circle and say, okay, for x squared plus y squared equals 4, find the equation of the tangent line. At, we'll say x equals 1. Okay, and the idea is that I can think about this as y as being a function of x. Okay, since we can think of y as being a function of x, we can treat y as a function of x even if we don't have a formula for it. Okay, so what we're going to do is think of y as an implicit function of x. Okay, now in some cases, I would be able to solve for y and get a single equation. Or in a case like this, I could solve for y, but I might need 2 different equations. Or in some cases, like we had back here, it's not possible to solve for y. And it doesn't matter. All of those we're going to treat the exact same way. We're going to say I can just think of it as being implicitly a function of x. I don't need to know the formula. Okay. So then what I'm going to do is I'm just going to differentiate. Okay, now when we differentiate, let me give you a quick example of a normal looking function. If I have something like y equals x cubed, and I want to write down the derivative, what I do is I say, well, on the left side, the derivative of y is y prime, and on the right side, I use my derivative formula, right? So that's how we write down a derivative. But what we really did is we took the derivative of both sides. So we differentiated both sides. So we're going to do the same thing here. I'm just going to differentiate both sides. Okay. So I'm going to think of this as the derivative with respect to x of x squared plus y squared equals the derivative with respect to x of 4. Okay. And then let's see what happens. Well, my derivative rules say you can break up derivatives over addition. So I'm going to write those as 2 separate derivatives, right? So I have the derivative with respect to x of x squared plus the derivative with respect to x of y squared. And when the derivative of a constant by itself is just 0, so I'll just write that here. The derivative of x squared I also know. That's easy, that's no problem. X is my variable. When I take the derivative of x squared, I get 2x. It's this derivative of y squared business that's tough. And what I'm doing here, again, let me give you an example of a different function that's maybe a little bit easier to understand. If I had a function for y, right? Let's suppose that y equaled something like x plus sine x, okay? Then to differentiate y squared, I could just think of this as x plus sine x squared, okay? And I would use the chain rule. Okay, so then I would take the derivative of the outside side, so the 2 would come down, inside stays the same, and then I would multiply by the derivative of the inside stuff. So let's try that same process here. My outside function is stuff squared. So the derivative of that, according to the chain rule, is 2 times the inside function to the power of 1 times the derivative, make sure that's a 1 and not a prime, times the derivative of the inside stuff. Well, if the inside is y, the way that I can write the derivative of y would either be y prime, or I'm going to use Leibniz notation and write dy dx. So then I have 2x plus 2y times dy dx equals 0. And the goal of my of my problem, I want to find the equation of the tangent line, so I want the derivative. Well, this piece here is the derivative of y. With respect to x. So I never actually found a formula for y, but now I have the derivative of y involved in an equation, and I can solve for it algebraically. Okay, so I'm going to subtract 2x from both sides. So we have 2y times dy dx equals negative 2x. And then I divide both sides by 2y. So I have dy dx equals negative 2x over 2y, which is just negative x over y. Now, I can't divide by 2y if y is equal to 0, but I can see that here in my end result. I didn't end up canceling that y, it's just hanging out there. So I don't need to worry about writing y can't be 0 because I can see that it can't be 0. Okay. So now we have a derivative. What did our problem ask us for? It said find the equation of the tangent line when x is 1. So what we need is a point now, and notice that I can't just plug an x value into the derivative. I need an x and a y. And that makes sense. If I go back, think about the graph here, the circle, if I only told you that x was 1, well, there are two different points on the circle, where x is 1, with two different tangent lines. So that's not enough information. Now, if we said x is 1, we could just give all the solutions, right? We could say, well, there's 2 points. I can find 2 tangent lines, one for each point. Okay, and that would answer it. But typically when we're doing implicit differentiation, if I want to find a slope or if I want to plug in, we're going to need both an x and a y value, because if I have a truly implicit function, then I need both an x and a y in order to find the point. Okay, and sometimes, so we'll just go ahead and find a y value. Okay. So for x equals 1, 1 squared plus y squared equals 4. So y squared is 3. So y could either equal square root of 3 or negative root 3. So I have these two different points. So we have 1 comma root 3, and we have 1 comma negative root 3. Okay, so for each point separately, let's compute the slope. So I'm going to show you, as we're doing this, the correct way to write notation. So dy dx is a derivative. Okay, so this is a function. Slope is a number. But it's the output of that function. So the way that we can write that, one way that we have of writing that is I could say the slope is the derivative, and then I can put a vertical bar, which means like when, right? So when I plug in, x is 1 and y is root 3. Okay, so then I get negative x over y, so negative 1 over root 3. Right? So then at 1 root 3, we have y minus root 3 equals negative 1 over root 3 times x minus 1. And I have the equation of a tangent line. Okay, and we can pretty this up a little bit. Distribute the slope, so I have negative 1 over root 3x, minus a negative is plus 1 over root 3, and then add root 3 to both sides. Okay, now there's a lot of arithmetic that you could do here to maybe combine things together. I'm just gonna say for our purposes that's unnecessary and distracting. What I do want to do is note that we had two different tangent lines. So let's go ahead and find the other one. So at 1 comma negative root 3, the slope is the derivative when I plug in x is 1 and y is negative root 3. And since my formula was, looking back here, negative x over y, I'm going to have negative 1 over negative root 3, which is a positive 1 over root 3. So then my equation of the tangent line is y minus negative root 3 equals 1 over root 3 times x minus 1. And we do our little bit of simplifying, but not too much. Okay. So those are the two tangent lines on the circle when x is 1. Okay, so let's sort of recap this and write out our process. Okay, the first step is going to be just differentiate both sides. All right. If I'm writing like y is a function of x or something like that implicitly, we want to make sure that anything that's an implicit function we treat as a function. Okay. So we want to keep in mind what our variable is. So mind the variable. If x is the variable, then everything else is a function of x. Okay, and if it's a function of x, then we use the chain rule on it. Okay, and I'm going to show you some examples. All right, the next step, after we've finished differentiating both sides, is we need to gather all of the dy dx terms. Okay, on one side of the equation. In our last example, there was only one dy dx term, so I'll have to make our next example a little bit more complex so you can see why this is going to be necessary. Okay. And then maybe I'll come back and fill in steps 3 and 4. Okay. So let's look at an example, and then I'll fill in steps 3 and 4, and you'll see why we need more steps. Okay. So here's an example. For x cubed sine y plus y equals 4x plus 3, find dy dx. All right. Our first step is to differentiate both sides. And differentiation works the same way as it always did. When I look at this, I say there are two multiplied functions here, so I'm going to use a product rule on this piece. Okay. So when I write it out, and I'm going to be very careful here, when I use the product rule, we take the derivative of the first piece times the second piece left alone plus the first piece left alone times the derivative, where x is my variable, of the second piece. Okay. Then I have the derivative of y. Oh, the derivative of y is just dy dx. Then I have the derivative of the right-hand side, and I don't really need a special rule there. The derivative of 4x is 4. The derivative of a constant on its own is 0. Okay, so we didn't leave anything out. We took the derivative of everything, and only the most basic derivatives did we actually work out. Any sort of product rule, chain rule, quotient rule, we break those into steps. Okay, now let's take care of those steps. I have the derivative of x cubed, so that's 3x squared. Sine y is hanging out. X cubed is hanging out. When I take the derivative of sine y, y is a function. It has its own formula. I don't know what that is, but it has its own formula. So I have sine of some function of stuff. So I'm using the chain rule. So the chain rule says, take the derivative of the outside function. So if I have sine of stuff, the derivative is cosine of stuff. I plug in the same inside function, and then I multiply by the derivative of the inside stuff. Well, if the inside is y, then the derivative of y is just, this is how I write derivative of y, dy dx. Okay. I got a little sloppy over here. Let me fix that. Okay, so since I have dy dx show up in more than one spot, that's why we have to gather all these dy dx terms. Now in this case, they're already both on the same side of the equal sign. But let's get rid of any extra stuff. So I'm going to subtract the 3x squared sine y from both sides. Okay. So then we have x cubed cosine y times dy dx plus dy dx equals 4 minus 3x squared sine y. Okay. Now I want to get dy dx by itself. It shows up everywhere in this left-hand side. So what I'm going to do is I'm going to factor it out. So that's this step 3. We factor out dy dx. So if I factor out dy dx, what I'm left with in the first term is x cubed cosine y, and what I'm left with in the second term is just 1. Okay. So then I can solve for dy dx by just dividing. So if I divide by all of this extra stuff, x cubed cosine y plus 1 on both sides, then what I'm left with is dy dx equals 4 minus 3x squared sine y over x cubed cosine y plus 1. Okay. So that's the process of implicit differentiation.